Today we are going to discuss current loop as a magnetic dipole. After that, we'll try to find out expression for magnetic moment associated with a revolving electron. We'll also see the relation between orbital angular momentum and magnetic dipole moment of a revolving electron. We'll try to find out expression for Bohr's Magneton and also what is its importance. So all these we'll be discussing in today's discussion. First, we are taking current loop as a magnetic dipole. Let's first of all take the expression for magnetic field due to a current loop. If we consider a current carrying loop, suppose it is the current I and the radius is R, its magnetic field at its axial line at a distance x, this is given as your mu naught by 4 pi to I pi r square by r square plus x square power 3 by 2. If we consider that the distance x is very large as compared to its radius, then it can be written as your mu naught 2 IA by 4 pi x cube. Pi r square, we can take it as the area of the loop. So this is the expression mu naught by 4 pi 2 IA by x cube. Now if you consider electric dipole, the electric field intensity on the axial line of the electric dipole, if you consider, then this is given as your 1 by 4 pi epsilon naught 2p by r cube 1 minus L square by r x square whole square. And again, if you consider a very small electric dipole, in that case its electric field on the axial line will be given as 1 by 4 pi epsilon naught 2p by x cube. This is the electric field intensity. This is the electric dipole moment. Now, if you just compare this relation, here you have the expression B, which is the magnetic field intensity, and this is your mu naught by 4 pi 2 by x cube. This is 1 by 4 pi epsilon naught is constant in case of the electric dipole dealing with the charges there. Here it is mu naught by 4 pi, which is also a constant, but dealing with the magnetic field intensity or magnetic field there. So this term I into A, this must be coming in place of some moment term. As here we have the electric dipole moment, so here we call it as the magnetic dipole moment. So magnetic dipole moment, if you consider for the current loop, we can take that it is like I into A. And its direction will be given by the vector A. That means it will be normal to this direction of the loop. So it will be acting in this direction. For a current loop where you have n number of turns, this magnetic dipole moment can be written as your Ni A vector. For loop of n turns. Now this particular term n into I, this is called as ampere turns. So what you can see that as we have the electric dipole giving electric dipole moment associated there, similarly current loop will also give a term that will be called as the magnetic dipole moment. So we can say that we can relate magnetic dipole moment associated with a current loop. Again, once you do the magnetic dipole, which we can treat similar to the electric dipole, there also on the axial line of the magnetic dipole, you will get a term which will be magnetic dipole moment there, which will be like product of magnitude of pole strength and the separation between the magnetic poles of the magnetic dipole. So here we get this term, which is your magnetic dipole moment associated with a current loop. Let's now take the case of a revolving electron. We'll try to see how magnetic moment is associated there. So suppose you have an orbit in which electron is revolving. Suppose we have the electron E revolving in this direction. That means we have taken the revolution of the electron in the anti-clockwise direction. And this is having a radius r. That is, the loop of this has the radius, or orbit of the electron has the radius r. If the electron is revolving in this direction, in that case, the current associated with this will be given by E by T. Suppose the electron is moving with the velocity v. So, because we have taken expression for magnetic dipole moment associated with the current loop as I into A, which is current and area of the loop. That is the product of the two. Here also, when the electron is revolving around the nucleus in its orbit, it means now it is also associating a current with it. If the electron is revolving in this direction, there will be a current associated due to this motion of electron. Of course, the direction of motion of the current, will be opposite to the direction of flow of electron. So if the electron is moving in the anti-clockwise direction, current will be in the clockwise direction. So here, if I consider the current associated as the charge divided by the time period of revolution, this we can write as E by 2 pi r by v. Because if I take the radius as r, in that case the radius or the length of the loop will be equal to 2 pi r, and if your speed is v, in that case the time period will be 2 pi r by v. So this we can write as E v by 2 pi r. And now if I take magnetic dipole moment, then this is your I into A. So this will be equals to EV by 2 pi r into pi r square. And now if you cancel the term r and pi, it is your EV r by 2. This is the expression for magnetic dipole moment associated with the revolving electron. And now let's see what will be its direction. If we consider that electron is moving in the anti-clockwise direction, obviously current will be flowing in the clockwise direction. So if the current is flowing in the clockwise direction, you can apply right hand thumb rule there. If the current is in the clockwise direction, thumb will indicate the direction of magnetic field. So in that case, the dipole moment will also have its direction in the downward direction. So this will give the direction of the magnetic dipole moment associated with the revolving electron. And this magnetic moment which we are taking, as it is associated with orbital motion of the electron, so we call this as orbital magnetic moment. So this is the orbital magnetic moment of the electron, and that is given as your EV r by 2. Let's now take orbital angular momentum of the electron. Now we know that angular momentum, this is given as your r cross p. So if the electron is revolving with the speed v, in that case, and suppose its mass is given as your me, so we can write orbital angular momentum as r into me, that is the mass of the electron and its velocity. So we'll have this expression for L. Now you consider here this r has this direction, v is in this direction. So if you consider the cross product of R and V, because this we can write as MER cross V. So this R cross V, if R is in this direction, V is here, so the direction of L or angular momentum will be in the upward direction. That means you can see this L and M, they are in opposite direction. So here we have a magnitude of L. If I take, this is your MERV, and M vector we have taken as EVR by 2. This we have obtained. So now if you consider M, this will be equals to, or M by L if I suppose take, in that case how much it will be? Your EVR by 2 divided by MERV. So this R and V will get cancelled, so you will get E by 2ME. So this is the ratio of M and L, that is orbital magnetic moment and orbital angular momentum. So this ratio is a constant. It is your E by 2 times ME, where ME is the mass of the electron there. It is constant. E, which is the charge of the electron, that is also constant. So this will be a constant there. So this term E by 2ME, this is a constant, and this is called as the gyromagnetic ratio, and its value is 8.8 into 10 to the power 10 Coulomb per kg. Also, we can get a relation for M vector that will be equals to minus E by 2ME and L vector. This will give the relation between orbital magnetic dipole moment and orbital angular momentum of the revolving electron. Now, if you take Bohr's quantization relation, then from Bohr's quantization relation, L, which is the angular momentum, this is integral multiple of h by 2 pi or nh by 2. Angular momentum, this is given as your nh by 2 pi. So angular momentum is nh by 2 pi. Now this term L we have obtained, and also the relation between magnetic dipole moment and angular momentum, we have just seen that it is M is your 2 by 2MEL. Okay, we are not taking its negative sign, that is related with the direction only. So, and now for this L, if I substitute, then it is your 2ME NH by 2 pi here. So this will give you E NEH by 4 pi ME. This is your M. Now you see this term E, which is the charge of the electron, H Planck's constant, 4 pi is already a constant, ME is a constant, mass of the electron. So this entire term, this is the constant, and this is your N, which is the principal quantum number. So if N is 1, in that case M will be equals to EH by 4 pi ME. Now this is a constant, and this is called as the Bohr Magneton. This is basically magnetic moment associated with electron in first orbit of hydrogen atom, because we have taken N1, and if you consider hydrogen atom, in that case you will get this relation. So in that case, this is the magnetic moment associated with electron in the first orbit of hydrogen atom. And if you consider its value, then Bohr Magneton will have the value 9.27 into 10 to the power minus 24 ampere meter square. So this is the value of Bohr Magneton. And we have seen that this is the relation which gives you magnetic moment associated with a revolving electron in the hydrogen atom in nth orbit, because here it is the n term there. Of course, when we take it for first orbit, in that case n will be 1, and then we get the value of the Bohr Magneton. Or you can say that we can get the magnetic moment associated with the revolving electron in any orbit in terms of the Bohr Magneton, because it will be n times of that. As you know that apart from the orbital motion of the electron in an atom, electron also have the spinning motion. So there is magnetic moment associated with that also. M, we are taking, suppose, magnetic moment associated with the revolving electron, that means due to its orbital motion. Will also have magnetic moment associated due to its spinning motion. So the net magnetic moment of the revolving electron, if you consider, it will be the sum of the two. So we have a magnetic moment associated with the orbital motion there, or angular momentum, that is your minus E by 2 me L, and magnetic moment associated with the spinning motion, that is called as the spin magnetic moment or intrinsic magnetic moment. So this is your spin magnetic moment or intrinsic magnetic moment. So if you now consider the net magnetic moment of the electron, in that case it will be the sum of the two, L plus ms. This ms we are taking as the spin magnetic moment there. So in that case you will get minus E by 2 me, and this is your L plus 2 times s. So this is your m. So the magnetic moment, if you consider for the revolving electron, in that case it will have both the magnetic moments there, magnetic moment associated with its orbital motion as well as magnetic moment associated with the spinning motion. So we'll get this as the total expression for the total magnetic moment associated with the electron. So this is all about the magnetic moment associated with the revolving electron, how it is related with the angular momentum there or orbital angular momentum there, and what is the total magnetic moment in terms of orbital motion and spinning motion. So the net magnetic moment will be the sum of orbital magnetic moment and spin magnetic moment, or that is also called as the intrinsic magnetic moment.